Good morning, everyone. My name is Haytham Sadeq, and today I will be presenting a presentation which is in course Transportation Engineering Impact in the University of British Columbia Department of Civil Engineering. I will be presenting a paper titled as the Predicting the Safety Performance Associated with the Highway Design Decisions, a case study of the Sea to Sky Highway done by Dr. Tarek and Dr. Paul D. Leur. Today I will be talking about an introduction of that project and this idea and the pilot project and the specification of that project, and then I will go to the methodology, what is the behind of this procedures, and what is the collision modification factor is, what is the collision prediction models that can be really used in some similar case study, and we will check the results and go to the economical analysis and conclusion and some comments and questions. As you know that the design decision is usually done by some technical guidance, which is the standards that we always use to really have some design decision and the quality of the engineering judgment. Now there is a new assessments, a new approach of assessment of objectives of the design consistency and the safety impact from changes in the road design parameter, and this is we can refer to the explicit evaluation of safety performance. And there's a lot of organizations that concerned about that, like the TAC Transportation Association of Canada and the Federal Highway Federal Highway Administration in the U.S. And they have a design domain which is really propose a comprehensive advice, and the quantification of safety impact is really introduced. And then the FHWA in the US has introduced the interactive highway safety design model, which we will use to get some values for the collision modification factors. For the section of Sea to Sky Highway, actually this was highway, this section is between the city of Vancouver in British Columbia and the Whistler, and which is called the Culleton Creek to Checkmas Canyon section. It has some difficult topography. We have limited budget for the highway upgrading, and it's around 6.9 kilometer section length, and it's a rocky, steep and mountain terrain. It has a difficult and costly construction and narrow lanes, minimal clear zone for the existing design, difficult horizontal and vertical alignment. The mean operating speed now is 75 to 80 kilometers per hour. Both preceding and succeeding sections for that sections in concern has a very high operating speed, which is around 100 to 110 kilometers per hour, and with an open and moderate terrain. The existing design of this segment has 33 curves and 26 tangents, which is a total of 59 subsegments, and the new design proposed was similar in the alignment for the existing, and it has a 2+1 lane cross section, 25 curves and 22 tangents, which is a total of 47 subsegments. The explicit safety evaluation for this project has some objectives. The first one is to determine the existing safety performance, to evaluate the expected safety performance for the new design, to compare the expected with the existing and identify location where safety can be improved, and evaluate the new design for the expected economical safety benefits. The methodology used in this paper was the explicit evaluation for safety performance. We will go for the steps. First, we will understand the project and the segmentation, obtain the input data, and we will talk about this input data, what is the input data for the safety analysis, and then select and apply the operating speed model to know what is the operating speed in that road, because the operating speed is different than the design speed, and then go to calculate the design consistency measure. And also we will talk in deep and about how we can measure this design consistency, evaluate the design and determine the inconsistency, and then select and apply the collision modification factor depending on the information before, and then go and select the base collision prediction model that is really suitable and appropriate, because this is a very important and sensitive step that you should really select a good choose for base collision prediction model. And then if there is requirement for any calibration for this collision prediction model, it should be done, and combine now the collision modification factor to the collision prediction model in order to get how much collisions we have per year, and identify the location that the potential for improvement, and then modify design to improve safety if required, and then go to re-evaluate, improve design, and estimate the collision frequency and severity distribution, and calculate the safety impact, and then summarize all the results. All this methodology will be trying to really explain it in a very simpler way. If we consider that this is the project that we have, we can divide it for some segments and give a naming for the tangent and the curves, and we can get for each segment of that, we can get a CMF for the lane width, the shoulder, and we will talk about these what is that, to get a collision modification factor, how much this change can change, how any change in the lane width can affect the collisions in this section. And then we will have some collision modification factor for the combine also design consistency in order to operate the speed and to check the operating speed and the side friction. We will combine all of them and select the base collision prediction model and then multiply the collision modification factor. So if for example we will have 40 collisions per year, if we have a very good section, we will have, this is less than 1, so we will get some less collision per year. If this is a bad design, we will have a collision modification factor more than 1, and we will get more collisions per year. And then we can sum the total collision frequency for all the sections in order to get how much collision per year for the whole highway we have. This is the methodology we used in this paper. What is the input data? We have to go to the segment length, the traffic volume, lane width, the shoulder width, the curve length in meter, curve radius, spiral length, gradient percent, super elevation, number of axis location per segment, and the percents of the three lane. The collision modification factor example, the collision modification factor for outside shoulder, for example, we can get it. There's a various type for expressing the collision modification factor. One of them is doing a chart for the collision. For example, when we have a very big shoulder, so we will have, for example, for 2000 annual average daily traffic, we can get 0.8 collision modification factor. If we have a very small shoulder or no shoulder, we will get very high collision modification factor. That means that it will increase the collisions if we have this case. And then we do this for all other input data. We can also use the IHSDM, which is Interactive Highway Safety Design Model, and the ISECR that can also give me some of the CMF values in a very nice software that can be, I already installed in my software. It's a free online software that you can use to get the CMF values. Also the design consistency measures, how we can measure it. First of all, we can subtract the operating speed minus design speed, so we get the 85%, which is the operating speed. So we see how much, if this is a big value, so this is a bad design. If this is a very small value, so the operating speed is a very near of the design speed, and this is the good design. Difference between the operating speed from one segment to the another segment, and this is also very important measure. The vehicle stability, which is the difference between side friction and the demanded friction, which is FR minus FD. We can get the value of FR, FRD, and V85, which is the operating speed, by using the speed prediction model and these equations. So if we have a very small difference, we have a very good evaluation. If we have a very demanded friction, if the demanded friction is bigger than the friction that is available, we have a minus value, and we have very poor design from a consistency measure point of view. Also, to convert this design consistency measures in order to get the CMF values for that, we can get a collision modification model also done by Dr. Said and Leur by the collision modification factor for the British Columbia, using this equation. And as you can see, there's a plus, because if this is increased, will increase the collision modification factor. But if for example this is the minus, if this is increase, so will decrease the collision modification factor, and this is will be having better design. And after that, continuing for the methodology, we will use the base collision model, which is this one, which which is a very important step, and it should be done in a very precise way because it will be affected by the local conditions. And the collision frequency based collision prediction model can be multiplied by the CMF, and then getting how much collisions per year we have, and for the total collision frequency we can sum for all sections and get how much collisions per year.